Bismillah ar-Rahman Rahim. Welcome to the lecture 15 of Discrete Structures CSC 102. In the last lecture we have studied set theory, and we have discussed some different properties of sets, and the properties of empty sets. We have also studied some set identities and the relationship between Boolean algebra and set theory. Today we are going to start a new topic, which is the relations in mathematics, relations of sets and functions. So in today's lecture we shall discuss some basic concepts of relations. We shall also discuss types of relations, means one-to-one relation, many-to-one relations, or some relations of such type. And then we shall discuss a relation on a single set or relation on a set. We shall also study the inverse of a relation, and we shall discuss the diagraphs, how we represent relations using diagrams, and at the end we shall discuss n-array relations. So first of all, before giving the definition of relation, let's discuss an example. Let P be a set of people. We have two sets P, where P is a set of people, C is a set of cars, and R is the relation which describes that this person derives this car. For example, if we have the set P, in set P we have people Carl, Susan, Peter and Carla, and we have another set C, which is a set of cars, Mercedes, BMW and tricycle. These are two sets. Now R is the relation between these two sets. What is this relation? Carl drives Mercedes, Susan drives Mercedes, Susan drive BMW, and Peter drive a tricycle. So there is a relationship between cars and the persons. Now let's define the relations. If we want to describe a relationship between two sets A and B, we can use ordered pairs. In mathematics we represent them in the form of ordered pairs, with the first element taken from the first set, here it is, and the second element is usually taken from the second set. In the relations we use two sets, therefore we call them a binary relation. Binary means two. So now the proper definition of relation: let A and B be two sets. A binary relation R from A to B is a subset of A cross B. Now what is A cross B here? We have studied in previous lecture the Cartesian product of two sets A and B. So here A cross B is the Cartesian product. So in other words, we can say that a binary relation R, we have R is always the subset of the Cartesian product of two sets A and B, and we use notation A R B. If R is the relation, then we denote it by A R B, means A is related to B, or we write it as A B ordered pair belongs to R. And if A is not related to B, we write it as A R, and we draw a line under the R, and we say that A B ordered pair doesn't belong to R. Now we take another example. If we have two sets A and B, where A is 1 2 3 4 5 and B is 5 6 7 8 and 9. Now we define the Cartesian product. As you know, we have written some Cartesian products of two sets in the previous lecture. On the same manner, we can write the Cartesian product of these two sets A and B. So Cartesian product of A B is A cross B, and we write the ordered pairs from the set A to the set B, means 1 5 1 6 1 7 1 8 1 9 2 5 2 6 2 7 2 8 2 9 and so on. At the end, with the last element, we write 5 5 5 6 5 7 5 8 and 5 9. So this is the complete Cartesian product of A and B. Now we define a relation R. R is the relation from A to B, and we define R as R is basically the rule which adds 4 to the first element and we obtain the second element. So here the rule is to add 4 in the first element of A. We get another element which is B here. So the first element of A is 1, we add 4 in 1, we get 5. The second element of A is 2, we add 4 in 2 and we get 6. Similarly 3 7 4 8 5 9. So this is a relation between A and B, and what is the relation? We add 4 in the first element and we get the second element in each ordered pair in R. Here we can see here easily that R is a subset of A cross B. So the relation is always subset of the Cartesian product of these sets. So we can also represent sets using such type of diagrams, in which this relation is basically the rule is to add 4 in the first element and we get the second element. So this relation which we have defined in the previous slide here, this is basically one-to-one relation. So one-to-one relation is basically in this type of relation, each element of A is related to exactly one element of B set. This is basically A set and this is B set. So in one-to-one relations, each element of A is related to exactly one element of B. So this type of relations we call them one-to-one relations. As you can see here, 1 is related to 5. If we add 4 in this, we get 5 in 2 6 3 7 4 8 5 9. So this type of relation is an example of one-to-one relation. Now we discuss many-to-many relations. If we have two sets, A, where A is the set of people, Ahmed, Peter, Ali, Javeria, Hamad, and B is the set of places, Paris, London, Dubai, New York and Cyprus. Now the Cartesian product of A and B, you can easily define it. A cross B is basically, we take Ahmed, Paris, Ahmed, London, Ahmed, Dubai, Ahmed, New York and so on. At the end, Hamad with Paris, London and Cyprus. So I hope you can easily write the Cartesian product between A and B. Now the relation is basically, rule is, or the relation is has visited. Now the persons in the set A has visited many places in B. For example, Ahmed has visited Paris. If this is true, we write it in an ordered pair in the relation. So if Ahmed has visited the Paris, then we write Ahmed Paris here in ordered pair. Ahmed has visited Dubai also, so we write Ahmed Dubai ordered pair here. Peter has visited London. Peter has visited New York. Peter has visited Cyprus, and Javeria has visited Paris. Also, Javeria has visited Cyprus. Hamad has visited Dubai. Hamad has visited Cyprus. So in this relation you can see that one person has visited many places and many persons has visited one place. Means this relation is basically the many to many relations. Means you can see in the figure here, Ahmed has visited Paris, so we relate them. Ahmed has visited Dubai, so we relate them here. Now Peter has visited London, Peter has visited New York, Peter has visited Cyprus. So you can see here that one person has visited many places, and for one place you can see here, to better for the better understand this, Ahmed has visited many places, so you can also see the Peter has visited many more than one places. And in Paris, this place has visited many persons. Paris has been visited by Ahmed, Javeria, Hamad. So you can see that we can relate one person to many places and one place to many persons. So such type of relations are basically many to many relations. So you can see that there are many arrows from each person and each place is related to many people. So such type of relation is basically the many to many relation. So you can see also R is the subset of A cross B, because A cross B contains more elements than the elements in the relation R. So the next is many to one relation. Such type of relations also exist, and in this case if we have two sets, the set A contains persons Bilal, Peter, Salma, Alia, George, Aziz, etc. So we have this set as set A and this set as B. B contains the weight, three weights, 62 kg, 64 kg and 66 kg. Now the relation is what is the relation? Relation has a weight of, basically you can say that, not mass, has a weight of 62, 64 or 66 kg. Now Bilal is a person. This Bilal has 62 kg weight. Peter also has 62 kg weight. Salma also has 62 kg weight. George, Alia has 66. George has 64. Aziz has 64 kg weight. Here you can see that many people are related to only one element of B. Here we have three persons who have 62 kg weight. Here we have two persons who have 64 kg weight. Here we have one person who has 66 kg weight. So you can see that many people are related to only one element of B, but one element of A is not related to many elements of B. So therefore this type of relation in which we relate many elements of the first set to the one element of the second set, so such type of relations are called many to one relations. In this case also you can see that this relation R, we can write the relation. How we can write R is equal to Bilal in ordered pair, Bilal 62, next is Peter 62, next is Salma, this is also 62, and next Alia has 66 kg weight, and so on. We can write the relation, this relation which we have defined here in this diagram or picture, whatever it is. So the relation we can write by using these arrows, these lines, because Bilal has 62 kg weight, so we write in ordered pair. Next, Peter has 62 kg weight, we write in ordered pair. Similarly this, and at the end Aziz has 64. At the end we can write here Aziz has 64. Then we can close this relation. So this relation is also obviously the subset of the Cartesian product of A and B, A cross B. So next is, we have studied until now the relation which are one-to-one, which are many-to-many, and then many-to-one relation. Now we have left only one type of relation, which is one-to-many relation. So the next is basically one-to-many relation. In this case, here we have the lengths. This set A contains basically the lengths 14 and 30 centimeter. Here in the set B we have this set: pen, pencil, ruler, needle and stick. So this is B set. We can define also the Cartesian product of A and B. Now what is the relation? Basically a relation is this: is the length of the object, B is the set of objects, A is the set of lengths 14 centimeter and 30 centimeter. Now 14 centimeter is the length of pen, 14 centimeter is the length of pencil. So pen and pen have same lengths, 14. Similarly 30 centimeter is the length of ruler, of needle, and 30 centimeter is the length of stick also. Now you can see here that we have related exactly one element of the first set A to the many element. Here we have connected or related two elements, or you can see that there is a relation between first element to the two elements of B. There is a relation of this element to three elements of this. Now you can see that one element of first set is related to the many element of the second set, but reverse is not true. So such type of relations are basically called one-to-many relations. So we can also define the Cartesian product of A and B, and we can also see that this R, which is a relation between A and B, is subset of A cross B. We can again write R as in ordered pairs 14 pen and 14 pencil and 30 ruler. Similarly at the end we can write 30 stick. So this is basically the relation between A and B. What is the relation? Relation is basically the length of. So we have studied four type of relations. First is one-to-one relation, next is one-to-many, next is many-to-one, and then many-to-many. So these type of relations, I hope you have understand these type of relations. We can again specify the relations, the four type of relations. Many-to-one relation can be expressed as this, because in this we have connected many to one. This type of relation is one-to-one relation because one element is related to one element in the second set. One-to-many relation means one element of the first set is related to many element of the second set. Many to many relation is basically we have connected one element to many elements, and one element is connected to many elements in first set. So such type of relation is many to many relation. Such type of relation is one to one relation. This is one to many, sorry, many to one, and this is one to many relation. So now we define relation on a one set or a single set. In the previous slides we have discussed a relation between two sets. Now what if we have one set? Means we define a relation between the elements of the set A. Now by definition, a relation on the set A is a relation from A to A. In the previous relations, how we denote the relation in definition, basically here. Let A and B be two sets, a binary relation R from A to B. How we denote it? We denote it like this. A relation R from A to B means A to B. We denote it like this. So the relation between two sets is usually denoted by this, like this. If we have one set, then the relation on that set is denoted usually as R, where R is a relation, and this relation is from A to A. Means relation is between the elements of A, but in the previous case we define the relation between the elements of A to the elements of B. But here now we define the relation between the elements of A. So in other words, a relation on a set is a subset of A cross A, like the previous definition of the set on a Cartesian product of A and B. Here the relation, if we define the relation on one set, then this relation will be subset of the Cartesian product of A with A. Means R is a subset of A cross A. If we see this example, if we have set A which contains 4 elements 1, 2, 3, 4, which ordered pairs are in the relation this, and we define the relation by this. Now what is the relation between the elements of A? A and B are related such that A is less than B. So we define the relation on the set A, means this relation contains all those elements, ordered pairs, in which the first element is less than second element. So there are 4 elements. We have 1, 2, 3, 4. Now we can say that 1 cannot come here because 1 is not less than 1. So here we can write 1, 2 because 1 is less than 2. Here we can write 1, 3 because 1 is less than 3. We can write also 1, 4 because 1 is less than 4. We can write 2, 1, no, we cannot write 2, 1 because 2 is not less than 1. 2, 2, no. 2, 3, yes. Next is 2, 4. We can write also because 2 is less than 4. Similarly we can write 3 and 4 because 3 is less than 4. We cannot write 3, 3 or 4, 4 because in this case this condition will not be true. So basically the relation R is this. So this relation contains 1, 2, 3, 4, 5, 6 elements, 6 ordered pairs, you can say that. So we can define the relation on R, or a relation on A, which is defined by this, like this, and the elements R contains as this, and this R is obviously the subset of A cross A, because A cross A contains more elements than this relation. So this is basically the solution. We can graphically or in the form of a diagram we can write this like this. So R contains these elements 1 2 1 3 1 4 2 3 2 4 3 4, because 1 is less than 2, 1 is less than 3, 1 is less than 4, 2 is less than 3, 2 is less than 4, 3 is less than 4. No other ordered pair can come in this relation because it doesn't satisfy the condition given in the relation here. Now you can see that graphically we can express it as 1 is related to 2, 1 is related to 3, 1 is related to 4. So this is basically one to many type of relation, you can say that, because one element here is related to many element in the second set. Similarly 2 is related to 3, 2 is related to 4, and 3 is related to 4. So this relation is basically an example of one to many relation, because we can also express is in this table form, in the form of a table like this. So next is basically how many different relations can we define on a set A with n elements. Now this is a question, that how can we know that how many different relations we can define on a set A with n elements, where A is the set with n elements. Now we have A set where A has, for example, x1, x2 and so on, xn, means A has n elements. N is some positive integer. A has 2, 3, 5, 10, 50 elements. Now first of all, we see that a relation on a set A is a subset of A cross A. We know this by the definition of the relation. We know that a relation, any relation, R, S, T, anything, on any set, on any single set A, is basically the subset of Cartesian product of A with A. Now how many elements are there in A cross A? Obviously we have n into n, because A has n element, this A has n element, so A cross A has n cross n elements, which is n square elements. There are n square elements in A cross A. So how many subsets? Now we basically, the relation is a subset of the Cartesian product of A and A. Now if we have a set which have n square elements, then how many subsets we can define from A cross A? So the number of subsets that we can form out of a set with m elements is 2m, as we know that by the basic set theory. The power set, we have studied the power set in the when we have studied the set theory. We have discussed that the power set of a set contains basically 2 power the number of elements of that set. For example, if we have m elements in any set, then the all possible subsets of set with m elements is 2 power m. So if this set has n square elements, then how many subsets can we define? This is obviously 2 power n power 2, or you can say that 2 power n square. So therefore 2 power n square subsets can be formed out of A cross A. So we can define 2 power n square different relations we can define on the set A. A relation on an infinite set. In the previous example we have defined the relation on finite sets, because A is here, basically A is the finite set. Now we are going to define the relation on an infinite set. The first and very very obvious relation which we usually discuss in the relation is the less than relation, which is less than relation for real numbers, means less than is this, you have already know this relation. And how we define this relation? Define a relation L from R to R, means now the sets A, the set A is basically the set of real numbers, which is an infinite set. Now for all real numbers x and y, x is related to y, where the relation is L if and only if x is less than y. Now this is the relation as we have discussed the less than relation in this example, in which we have chosen the set A to be finite, which contains 4 elements. Now the same relation we have defined on the set of real numbers. Now the set A is basically this in an infinite set, and the relation L between the elements of R is basically, if we have 2 elements x and y of R, then x is related to y if and only if x is less than y. For example, if we say that is 57 is related to 53, no. Why? Because 57 is not less than 53, so 57 is not related to 53. Similarly, this is basically minus 17 is less than minus 14. This is true, so minus 17 is related to minus 14. This is yes. Next is 143 is related to 143. No, because 143 is not less than 143. So 143 is not related to 143 under this relation. Next is minus 35 is related to 1. This is true, because minus 35 is less than 1. So we can say that minus 35 is related to 1. Now if we want to draw the graph of L as a subset of Cartesian product, Cartesian plane, basically Cartesian product here is basically the Cartesian plane, because if we take the Cartesian product of real numbers, we have the set of real numbers as this line. If we take the Cartesian product, we get the plane, where here we have x, here we have y. So how we can define this relation on the Cartesian plane, because this relation will be the subset of the Cartesian plane, because A cross A, the R relation R, not R, L. The relation L is basically, the relation L is basically x is related to y if and only if x is less than y. Here basically the relation L is subset of R cross R, where R cross R is the Cartesian plane. Now we can express L on the Cartesian plane as a subset of R cross R. Now for each value of x, all points x, y such that x is less than y, or we can say that x is less than y or y is greater than x, these both things are same. On the graph we can express this like this, because in this region y is always greater than x or x is always less than y. So this is basically the relation L, you can say. So graphically we can express this relation like this. We take another example so that we can understand well how we define the relation on an infinite set. And the congruence modulo 2 relation, we have already studied the congruence relations, congruence modulo relations, in which in the previous lectures. How we define it? Define a relation E from here. Now the relation is denoted by E. we can define the relation by any capital letter, for example R, L, E, S, T, anything. So here now the relation is denoted by the capital letter E from Z to Z. Now what is Z here? Z is basically the set of integers. Z is the set of integers which is 0, plus minus 1, plus minus 2, and so on. So this is basically the set of integers. Now what is relation? For all elements M belongs to Z and N belongs to Z. M and N may be different elements. M is related to N if and only if M minus N is even. So this is a relation which we define between the elements of Z. How M is related to N? M may be different element, N may be different element. These both elements may be same also, because M is also the element of Z, N is also the element of Z. These two elements can be same, could be same, or could be different. So what is the relation? M is related to N if and only if M minus N is even. Now is 4 is related to 0? 4, we can check 4 minus 0 is basically 4, which is even. So this is true, this is true, or this is yes. Is 4 is related to 0? Yes, 4 is related to 0. Now the second case is 2 is related to 6. 2 minus 6 is basically minus 4, which is again an even number. So this number is 2 is related to 6. In this case 3 minus minus 3 is basically 6, which is even. So this is also true, that 3 is related to minus 3. In the next case 5 is related to 2. 5 minus 2 is 3, which is odd. So 5 is not related to 2. This is false. Or you can say that this 5 is not related to 2. We can write it as 5e not related to 2. You can just cross the relation here to mention or to show that 5 is not related to 2. The next case is list 5 integers that are related to e to 1, that are related by e to 1. Now 5 integers, we can take 1, 3, 5, 7, 9. Similarly we can take as many as integers which are related to 1. There are many such lists in which we can give 5 integers which are related to 1, but here is a list of 5 integers: 1, 3, 5, minus 1, minus 3. Basically 1 minus 1 is 0, where 0 is considered to be even, as you know. So 3 is related to 1 because 3 minus 1 is 2. 5 is related to 1 because 5 minus 1 is 4, which is even. Minus 1 is related to 1 because minus 1 minus 1 is minus 2. Minus 2 is even. Similarly, minus 3 is related to 1 because minus 3 minus 1 is minus 4, which is even. So this is a list of 5 integers. We can give some other integers, list of some other integers which are related to 1. So the last case is prove that if n is any odd integer, then n is related to 1. Now, and the last part, we have to show that if n is any odd integer, then n is related to 1 under this relation. So now we have to show that, prove that here, if n is any odd integer, then n is related to 1 under the relation this is the relation. How we prove it? We prove it by direct method. We suppose that the hypothesis in this case, this conditional statement n is an odd integer, then we have proved that n is related to 1 under the relation E, where E is m minus n is even. So we suppose that the hypothesis of this conditional statement, universal conditional statement, is true. We prove it by using the direct method. Suppose n is any odd integer, then n can be written as 2k plus 1. Obviously you know this. For some integer k, where k is any integer which belongs to z, k. Now by definition of E, by the definition of the relation E, n is related to E if and only if n minus 1 is even. Now we have to show when this n will be related to 1. If we can prove that n minus 1, because m is related to n if m minus n is even, so n is related to 1 if n minus 1 is even. So this is what we have to prove, that n is related to 1. So we have defined n like this: 2k plus 1, n minus 1 will be 2k plus 1 minus 1. So 1 cancels with 1, we get 2k, where k is some integer and 2 is basically, we have 2. Any integer which is a multiple of 2, that is always an even integer. Therefore n minus n is an even integer. So because 2k is even, 2k is equal to n minus 1, therefore n minus 1 is even, and hence n is related to 1. This is true, hence the proof has been finished. Next, a relation on a power set. You know what is the power set? The set of all possible subsets of a set is called the power set, which this power set contains also the empty set we have discussed in the previous lectures in the set theory about the power set. So if we have the set X, which contains 3 elements A, B, C, and its power set contains 2 power 3, because 3 is the number of elements here in this set. 8 elements. Its power set will contain 8 elements. So here is the power set of X: 1 2 3 4 5 6 7 8. So it contains 8 elements. Now we define the relation, a relation S from P of X to Z, as follows. Now this relation S is basically from how we can denote it. S is from P of X to Z. So this is how we can denote this. What does it mean? S is a relation from P of X to Z. For all sets A and B in P of X, A is related to B if and only if A has at least as many elements as B. So this is basically the relation. This is how 2 elements of P of X are related, and we obtain the element of basically here 2 elements. Here sets are elements of the power set, because here power set is basically the set of sets. So now therefore we define the set A is related to set B under the relation S if and only if A has at least as many elements as B. So A has at least as many as elements as B. What does it mean? That number of elements in A are either equal or greater than the number of elements in B. This is what this relation means here. So we can see here in the first part, A is A B set is related under this relation S to this set. These 2 sets are related or not under this relation S? Yes. Why? Because number of elements in the first set A is 2 and the number of elements in the second set is also 2. This is greater than or equal to this. So the number of elements in the first set means A has at least as many elements as B. So this is true because A has 2 elements and B has 2 elements. Now this is relation is because yes, this is basically A is related to the empty set because A has 1 element and empty set has 0 elements. So 1 is greater than or equal to 0. This is true. So A has at least as many elements as B. So the number of elements in A are greater than or equal to the number of elements of B. So this is true. In this case, the number of elements in the first set is 2, in the second set is 3. Now this is true? No. 2 is not greater than or equal to 3. So this set BC is not related to the set ABC because the first set has not greater than or equal to number of elements as in B. This set, in this case, the first set has 1 element, second set has 1 element. This is greater than or equal to this. This is true. So these two sets are basically related under the relation S. So this is how we can define a relation on the power set. The next is the inverse of a relation. In the previous slides we have discussed the different type of relations, a relation between two sets A and B, a relation on a set from A to A. Now we shall discuss how we define the inverse of a relation. If we have our relation R from A to B, here we have R is the relation from A to B. How we denote it? We can denote it R from A to B. So then, as by name, the inverse of a relation, we define R inverse. Here we write R power minus 1. We write it like this. This is basically, this is not true. This is written as R power minus 1 and read as R inverse. This relation is basically from B to A. As we define here, relation from A to B, R inverse is from the second set to first set. As by the name, this is basically the inverse. Then the relation R inverse from B to A can be defined by interchanging the elements of the all ordered pairs of R. This is basically an informal definition of the inverse of a relation. And how we denote it? Now the proper definition is this: let R be the relation from A to B. Then we can define the inverse relation R inverse from B to A as follows, like this. This is basically yx belongs to B cross A such that xy belongs to R. Means R inverse is basically the subset of the Cartesian product B cross A. You can say that R inverse is subset of B cross A. R inverse is subset of B cross A. So as R is a subset of A cross B, R inverse is a subset of B cross A. And any element in R inverse, which is an ordered pair yx, this element belongs to R inverse only if xy belongs to R. Means that we can only interchange the elements of R, not the Cartesian product A B or A cross B or B cross A. Or equivalently, we can say that for all x belongs to A, y belongs to B, yx belongs to R inverse if and only if. Here we have if and only if xy belongs to R. If xy doesn't belongs to R, then we cannot write yx belongs to R inverse. This is basically R inverse. So I hope you understand what is the inverse of a relation. In inverse of a relation, we write the elements of R inverse. We interchange the elements of R only. We take an example of the inverse of a relation. In this example, we choose the finite sets. Let A is basically a set which contains 2, 3, 6, and B is the set which contains 2, 6, and 8. And let R be the relation which divides. R is the relation. Divides means any element X of A is related to any element Y of B if and only if X divides B. Oh, sorry, X divides Y. X divides Y. Then we say that the elements of A are related to elements of B. How we can write R, the elements of R and the elements of R inverse. First, we shall write the elements of R. Now the elements of A which divides element of B, we shall write in the relation R in the form of ordered pairs. We choose the first element. First element divides the first element of B, yes, so we write an ordered pair 2, 2 here. Now the first element of A divides second element of B, yes, so because 2 3s are 6, 2 divides 6, so we write ordered pair 2, 6 here. In this relation, we take the first element of A and the third element of the set B, where the first element, this 2 divides 8, yes, so we write ordered pair 2, 8 in R. Now we choose the second element. Second element of A divides first element, no, because 2 doesn't divide 3, 3 doesn't divide 2, but 3 divides 6, the second element of B, so we write here an ordered pair 3, 6. Now second element of A 3 and the third element of B are not related because 3 doesn't divide 8. Now we choose the third element of A. It divides 2, no, because 4 doesn't divide 2. 4 divides 6, no. 4 divides 8, yes. So here are the elements of the relation R. Now how we can write the R inverse? If we, there are two methods, there are several methods. You can say that we can write R inverse directly by interchanging the placement of the elements in the ordered pairs in R. Here R, we interchange the elements in the ordered pair. Here we write 6 here, 2 here. Here we write 8 here, 2 here. Here we write 6 here, 3 here. Here we write 6, 8 and 4. So by interchanging the elements in the ordered pairs, we can directly obtain the inverse of this relation. There is another way. We write the inverse of this and then we define this. So for all y, we can define for all y x belongs to B cross A, y is related to, now here we have interchanged. Here we have x divides y, sorry, x related to y. Here in R inverse, y is related to x under the relation R power minus 1 or R inverse. If and only if, now here if x divides y, then y is a multiple of x. So y is a multiple of x is basically the inverse of this relation. So we can again write the R inverse, which will be same as this. Graphically, if we have the relation R, which we have defined in the previous slide, 2 is related to, basically this is R, 2 is related to 2, 2 is related to 6, 2 is related to 8. So 2 is related to 2, 2 is related to 6, 2 is related to 8. Graphically, we can express the relations like this. Here we write set A, we write the elements of A. Here we write B set and the elements of B. Here we write the R, and R we know that this is R. Now in this relation we have 2 is related to 2, 2 is related to 6, 2 is related to 8. So we mark arrows from 2 to 2 to 6 to 8. Similarly 3 to 6, 3 is related to 6 and 4 is related to 8. So this relation is also one to many. The type of this relation is also the one to many relation. Now how we define the inverse of this relation? We just interchange the direction of the arrows. This is how we can define the R inverse, or we can define the R inverse again. Here we have just interchanged just change the direction of the arrows. 2 is related to 2, 6 is related to 2, 8 is related to 2 as this, and 6 is related to 3, 8 is related to 4 under the inverse relation. Either we can draw the picture or graph of the inverse relation like this, or we can redraw this. Write B first and then A. We write the elements of B, we write the elements of A, and we draw the arrows between the elements which are connected. This relation is basically many to one type relation. So here you can say that 2 is related to 2, 6 is related to 8 is related to 2, and 6 is related to 3, 8 is related to 4. So this is how we can define the inverse relation between two sets. In the previous slide we have taken the finite sets to discuss the inverse of a relation. Now we choose an example which have infinite sets. Now we have to define a relation R. This basically R is written in italic form, which represents a relation, and R which is written in the bold form, represents the set of real numbers. Now for all x, y belongs to R cross R, x is related to y if and only if y is equal to 2 absolute value of x. We have already discussed the absolute value function. Draw the graphs of R and R inverse in the Cartesian plane, because the relation is basically the subset of R cross R, which is a Cartesian plane. We have discussed it in earlier slides. Now how we can draw the graphs of R and R inverse. If we see, just for the better understanding, that what kind of elements are in R and what kind of elements are inverse, we can choose some elements at random, 1 plus 0, 1 minus 1, 2 minus 2. Then the corresponding elements of y are like this, and the inverse of this relation is basically just we obtain by interchanging the elements here. Now in Cartesian plane we can draw the graph of this y is equal to 2 absolute of x like this. This is the graph of absolute of x, because for two values of x we have one value of for two values of x we have one value of y. So this is how we can define this relation. Now if we interchange the elements, basically in R inverse we interchange the elements y, x, such that x, y belongs to R. So in R inverse we have to interchange the place of elements in the ordered pair. If we interchange the place in the ordered pairs here in the R inverse, then the graph we shall have like this. Now we have, for two value of y we have one value of x. This is how we can draw the graph of R inverse in the Cartesian plane. Basically this graph is rotated here in this form. For today It's enough, I think, and we have discussed the inverse of a finite relation, and then inverse, how we take the inverse of an infinite relation. For today, it's I think it's enough, and in the next lecture we shall study the remaining part which we have, which is the representing relation using digraphs. This we shall discuss in next lecture. For today it's enough, I think, and we stop until here. So today we have discussed some basic concepts of the relations and types of relations. In types of relations, we have studied one-to-one relations, one-to-many, many-to-many, and many-to-one relations, and then we have defined the relation on a single set. We have discussed the less than relation, the congruence modulo 2 relation. We have also discussed the inverse of relation. These two topics we shall discuss in the next lecture, because today the time is short. So until the next lecture, Allah Hafiz.